Hey, okay. So let's see. Today we're gonna do the bronze USACO Open. Um, this is the final contest of the season. We're gonna go through it and see what it's like to solve the problems. Of course, I have not seen these problems, and we're gonna see how it goes. Uh, let me share my screen real quick. Oh, US Open is generally a bit different because, of course, now there's usually one extra hour, and the problems are meant to be the hardest of the season. Let's share my desktop. Okay. Okay, so hopefully you can see everything. Um, we'll get started. Okay, we'll take a chance to read the problems. So we're going to end cows. We want Guernseys in even numbered positions. And we can reverse even prefixes of the cows. And so not only do you want to achieve a set of reversals, like we want to know the set of, we don't necessarily want to know the set of reversals, but we want to know the actual minimum of reversals. So this is one of the problems. This might be some of the greedy solution. Let's see. Yeah, we'll come back to that. Okay, so in this case, we're given second problem, counting liars. Okay, so we're given n cows that each tell us Bessie is at a location less than equal to pi or greater than equal to pi. Um, so we know if they're telling the truth, you would get some range from a point pi that's actually in the input. So I think we can treat this, since there's only 1,000 points input, I think we might have some ideas here. We'll come back to it though. And then the third problem, alchemy. So you have 100 metals or n metals up to 100. You have some number of them up to 10 to the 4. So of these problems, number 2 seems like the one I want to think about just because I think we have some ideas here. So this is kind of liars. So the first thing I would notice is that we have n less than equal to 1000. This implies O of n squared might pass. And 2, if some set of cows didn't lie, so the set of cows that didn't lie, the range where Bessie could be would be, if we have these PIs, it'd be some PI less than equal to Bessie less than equal to PJ. So even if we, okay. So I think the idea is we might want to be able to try every possible range PI to PJ because there are n squared of those. But then we have to worry about the number of cows. We can instead look at like adjacent ranges where PI and PI plus 1. Because Bessie being in between any of those locations is the same at being either endpoint. We could treat the cases where she's at the endpoint separately. We might need to, because those have more than one way the cows could say to make those count. But every point in between, like PI and PI plus 1, if you sort the PIs, are essentially equivalent. Like there's no way to differentiate them. So we can try all possible locations for Bessie based off whether she's between 2 points given or she's at a point given. So if she's at a PI or between a PI and a PI plus 1, we could then try to figure out how many cows are consistent with that. And the minimum ones that aren't consistent with that must be lying. And you just take the minimum for all ones. So there'd be like O of n, and it takes O of n time to check as well. So we'd get something that's, in this case, we would try, our idea is to try all possible locations for Bessie and check if cows are consistent, and which ones are not consistent. You have to throw them out and say they're lying. You take the minimum of that over all of them. So we have the one observation. If Bessie is in a like that open interval PI comma PI plus 1, then they're all equivalent. Doesn't matter where she is in this range. So this should be a pretty quick one to implement. USACO counters, you don't really need to rush to implement. It's perfectly fine to also read the other problems. So maybe here it'd be worth thinking about the other problems. So I want to look at this one real quick. Yeah, I don't really have a reason for bringing this one. That one, it just seems interesting. I don't know the answer to either problem 1 or problem 3 yet. So this one is Photoshoot. I'm just going to write down the sample input really quick so we can look at it. It's G, 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 H, G, H, H, G. And in this case, we have 14. So what is invariant I'm just trying to think what doesn't change or does change when we actually do a reversal of prefix. Um, hmm. Okay, so what are the reversals do here? We can actually just do one reversal. Oh yeah, we want G's at even positions. I forgot, not H's. So it's okay. So this is an even position, so we wouldn't really want to touch these. But this is the next even position, and I wonder, is it possible to get a G there? It is. So what happens if we just do this greedily, where maybe we do a reversal and we look at this, we get H, H, G, H, H, G, H, G, 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 H, G. This is even, and this is even. I think I messed up the reversal here. We should have lost N, A, H, H, G, 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 H. Oh, yeah. Okay. H, G, 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 H. So we got the last one to be G, H, G, H, G, which is so we kind of want the next one to become oh yeah, we can't reverse any prefix. We can only reverse even prefixes. Otherwise, you can rearrange the list as if you want. So that would not make sense. Okay, so if we do go greedily, we can only look at the even position. So we can do that transition. And then we're left with, oh, this G has to be stuck here. You can't move it out without moving out the other G. So I feel like you might just do this. 5. Okay, so that's not optimal. I want to find the minimum number of persons needed to do this. So in this case, this reversal should be non-optimal because we can do one more reversal. We can do H, G, H, H. We reverse this section, reverse here, and then here. And that really would get you to 6. And I feel like we could prove that this probably gives you the optimal number, but it definitely doesn't do it in the minimum number of moves. And we can see that that fails the sample. So another thing to notice is that like pairs stay together. We can reorder and flip pairs arbitrarily, but they're stuck. So in this case, if we look at like the original input, we have, let's see, we have GG, we have GH, we have GH, HG, HH, HG, HG. You cannot flip the HH for sure. And so you know you're stuck. You can flip all the other ones arbitrarily. You can arbitrarily order them. You can arbitrarily flip them, I believe. Wait, can we arbitrarily flip? Yeah, you do like if you wanted to arbitrarily flip, like if you want to flip this one only, you would do the entire permutation, flip to the start, and then flip the entire thing back. So we know how to compute the optimal. We just count the number of pairs that have a G in them. The number of pairs that have a G. This is one observation we can make. The number of pairs with a G equals the max number of G's possible on even positions. So then we'd look through. Maybe this would work greatly. If we were looking here, we would see, okay, which ones are invalid. We don't really need to touch the ones that are valid, right? We want to prove this, but this one, they're all stuck, right? HH you can't change, HG, HG are actually good. HG is good, GH is not good. So this one is an issue. We want to flip it. This one needs to be flipped, and this one is good no matter what. So we can ignore. So we have ones that we either don't care about, so we can remove them. So we can look at only the pairs that have a GH or an HG, and we know which ones need to be flipped or which ones can't be flipped. And so I think it's the number of times we switch between needing to flip and not being flipped, because you can flip. The algorithm would do, this is the idea. So we look only at pairs of HG and GH, because the HHs can't be flipped and the GGs can't be flipped, and so they don't affect the maximum possible. And so in this case, we look at the pairs HG and GG, and we can look at this as a binary sequence of ones that need to be flipped and don't need to be flipped. So we get some sequence of like 1, 1, 0, 0, 0, 0, and you want to make them all 0. 0, but we can flip and negate a prefix. Of course, the zeros at the end you don't want to touch probably. And then we flip 1, 1 and we're done, right? So you look at the prefix of the ones, so those the only one that flips. Let's say we look at another example. Let's look at like you have like 0, 1, 0, 1. We know we have to flip the 1. So one choice is we can do 0. We'll flip and negate. Flip and negate actually gives you the same sequence. If you flip the entire thing, we need to get that last 1. Another option is to go from the front. We would flip and negate 1, 1. Right, so we get 1, 1, 0, 1. Now we get I guess that's no. I guess we start with a 0, we want to make it a 1. And then here we want to do 1, 0, 0. And we can do 0, 0, 0, 1. And you get 1, 1, 1. There's at least one way to do it. This feels like way too many flips. 5 flips. I think notice n is up to 2 times 10 to the 5. Okay. Just making sure I remember that. So one greedy possible choice is you take the first contiguous sequence of 0s and 1s and you make them match the one after. I don't think I did that correctly. Let me rewrite the greedy solution I'm describing. And I don't know if that's optimal. I haven't actually proved anything. Not 100% sure. We get 0, 0, 0, 1. 1, 1, 1, 1. So this is 4. Seems reasonable. You do know you need to flip at least 3 here. Actually 4, because you have to flip between all the ones where it switch, and you have to flip at the end because it's a 1. So actually, I believe you have to flip this 4 times, provably. But otherwise, these are always going to be flipped together if you never split them down the middle, right? They'll either not flip or both flip. So you have to cut some point down the middle of these two. Same with these two and these two to separate them. You'll move them, but they'll either get moved together and stay separate, or be moved together. They have to be flipped separately. Otherwise, they get stuck together. And then the last one also has to be flipped. And the only way to flip that is if you flip the entire list. So 4 is optimal. The other thing we can, okay, I guess, so if it's, I think that actually proves the answer for the case, like an even number that's like, okay, so we have a few cases. We have 0, 1, 0, 1, 0, 1. This is, let's just say these lengths are like k numbers. This should be just k, right? Let's say we have 0, 1, 0, 1, 0, 0, like 1. So say it's k is odd and it ends in a 0. In that case, you probably have to flip k minus 1, I think. And it's possible because you can just really do it like we saw. And then if we have 1, 0, 1, 0, 1, 0, this is again probably k minus 1. Let me double check. So we look at 1, 0, 1 0 0 0 0 1 0 1 1 1 0 0 0 0 0. That is 3 flips. Probably k minus 1. And if we have 1 0 1 0 0 0 1, so it's odd, we should get k minus just k. Okay. So it's the number of like switches from HG to GH, ignoring HHs and GGs. So the idea I think we could do is count number of switches from HG to GH when we're looking at the pairs. Like if the last GH pair you saw was an HG and then you see a GH, you have to flip. And you want to know is the last one, if last pair is HG, then subtract 1 because we don't count the last pair. And if they're contiguous, we always flip them together, I believe. You don't ever cut those, and that would still work. So this should give us a solution. This one, it's a cute problem. I do like that problem. I think that will work. I think we prove it's optimal just because we can see that the degree solution would get that too. And of course, you have to provably use at least that much. Because every step you remove like 1 switch. So, okay. So I think at this point, we should try implementing one of these. I guess we can go back to do counting liars. Let me rearrange this. Okay. We're gonna do it in C++. We'll start by creating a C++ file. We'll create a basic template. Okay, so we do have to take in the input. So we're going to write out a little plan. So take in the input. We need to sort the inputs by increasing pi. So now we want to, the idea, we want to try all locations for best. So 1, we want to try all pi locations. Try all between pi and p plus 1 locations. These are the 2 cases. In each case, probably we want a function that check whether how many cows are lying, and then we'll output the minimum liars we saw in any of the. So this is kind of an outline. Of course, with USACO, taking your time, implementing slowly, like really won't hurt you. It's not a contest that penalizes taking your time. And in fact, implementing rushing implementation probably will lead to more bugs. So you should take advantage of it. So one, we need to take the input. So we have in n the number of cows. And then we, so in this case, we will create a struct to store count. This will make it easier to sort. So if you're not familiar with this in C++ or Java, make sure you're familiar with how to. So we could use a pair, but I'm just gonna make a struct because I like having a struct. So in this case, we'll give it the value p. And then Boolean less than. Actually, we'll just do the car. or less than. Okay. So we're gonna need to store these cows. We can just store them in an array. You could also use a vector if you want. But I'll use an array. In this case, we have up to 1,000 cows. So we need to take in these cows. We haven't set them yet, and we're also going to figure out how to sort them. So sort cows by we're going to take the input. We need to take in the number of cows, and then one cow. So in this case, we're taking cows by dot dir, and then cows by dot p, because that's the order they come in the input. So we're going to need to write a comparator. If you're not familiar with how to do this in C++, you can do operator overloading. You have to override the less than operator. You take. So you have to make sure to not forget the constant. If you forget the constant, it won't actually compile, or it won't recognize it as the comparator. So in this case, we just want to return p less than other.p. So one thing to notice, we can have duplicate pi, but this doesn't matter. And if there's no pi and pi plus 1 are the same, there's actually nowhere in between to try best. So we need to make sure to skip. Make sure to skip pi equals pi plus 1 cases. So if they're the same, we want to ignore them. So we have our comparator. So we're going to make sure to sort them cows and cows plus. So we want to try int possible Bessie equals in this case, we want to try this location. So we want to keep track of our ants. So in this case, we make ants. We want to know the minimums. We want to set this something big. If Bessie is completely out of bounds, we know like all the cows could be lying, but no more than n. So it doesn't matter where Bessie is, but maybe they're all lying. It could be n. So we want to update ants if it's better. So the number of liars, let's say we make a function that says count liars, and we pass it in possible Bessie. Ants equals min, ants count. So in this case, we have to write this count liars function. Int Bessie. So we're going to try putting Bessie here. We want to know how many are consistent or not. So we need to check all cows. Over all cows. Boolean lying. So if cows by.p the only ways they can lie is if you're less than Bessie and then cows by dot. So there's two cases to be lying based on whether cow G or L. So it says that it's greater than equal to, sorry, we need to flip this direction. Or we can go with less than. So we say it's less than equal to, but Bessie's actually greater than. So this is actually a lying cow. The other case, cows by dot p is greater than Bessie. And kind of add up there equals G line. We want to make sure to double check these are greater than, less than, not less equal or greater than. Because otherwise, like you're not lying if you're actually equal to Bessie ever. So that's a sanity check. We know that should count. So we can keep track of count. And so if lying, liars plus plus, I just return liars. So this function should help us. And I believe that will work for this case. Now, we're going to loop over all the positions. We notice we don't need to try all locations in between, just one. So we can pick any one, and we'll just pick like pi minus 1. We start at 0, so we don't skip the first. Bessie is before everything. So I assume Bessie is allowed to be at a negative location. I assume it's not an issue. Just double checking. So int possible Bessie equals count liars. Yeah. So don't forget if Bessie is greater than everything. In this case, one extra case. Cows of n minus 1 dot p plus 1. Okay, the number of liars is the count liars possible Bessie. The ants and ants equal min, ants liars. In this case, we'll just output ants. I think this works, but we'll see. At the input, that is 0. Good sign. Of course, so it could be completely wrong, but we'll see. In this case, we're given 2. I mean, that's a good sign. This might be worth submitting. We still have plenty of time to debug it, and submissions never hurt us in USACO. So if you have the let me find where it is. Feel free to submit as a way of debugging too. So submit and see how this goes. It's possible we have a bug, but there's really no harm in submitting. Okay. Yeah, got it. So that's one problem done. We obviously knew how to solve it earlier. We just didn't try it right away. Okay. Now, I think we should. I like having a time to think about the problems first before implementing, just because maybe you have thoughts in the back of your head and you never want to forget to read a problem or get too focused on one problem. So I think we'll just read the next one, because this is the last one we don't know how to solve, or at least believe we don't know how to solve. Obviously, we haven't. I mean, I think we know how to solve the first one, but we have not got it correct yet. Okay, so you just want to have the most number of metals in general. You don't actually care which type of metal. So some number of recipes. you can like merge sets of these together. Like for example, you merge a 3 and a 4. But you always get a bigger metal, which oh, sorry. For some reason, I kept reading that as maximum number of units of metal, and I didn't see the N. So I was like, well, you wouldn't want to apply any recipes if you maximum number of units of metal. So okay, so in this case, we have alchemy. So we want the maximum units of metal N. So N is pretty small. Yeah, we just want to know how many units of metal N we can make. So I feel like, if you can make a metal N with some recipe, well, it's not necessarily optimal to greedily use the recipes because it's possible there's a recipe that uses less. Oh, but we do have, it is guaranteed that for each metal, there's at most one recipe to make it. So there's only one make metal N. So you would like to make as many of the constituent parts of metal N as possible. But then you're looking at the constituent parts. You don't want to overuse, like, you don't want to make too many 4s when you could have made, like, when you didn't need to or something. If you need 3s and 4s to make 5s, maybe you can make both 3s and 4s from 1s, but you wouldn't want to use them all, right? So in the case, we can like do this step by step. Like we want to make one metal N. If you want to make exactly one, maybe you could binary search, but let's just say you want to make exactly one, and we're just going to update our metal counts. And you make exactly one, you need a 3 and a 4. Well, if you have a 3 and a 4, you're done. If you don't, you need at least one 3, you need at least one 4. And you would try to check, can I make both? It doesn't matter which one you do first because you're doing it step by step, so you don't overmake an ingredient. I think this should work, but the issue is there are 10 to the 6 units of metals that you have to start with, and that could be a bit slow. So in the end, the most you can make of metal and is 10 to the 6, right? Because you can only start with 10 to 6 metals and you never increase your metal counts. So what we might want to do is possibly binary search on we might want to binary search on the number we want to make, and we just see, can we make that many of 4, can we make that many of 3, and so on. Because it's easy to check the possible. You take as many as you already have, and then you would recurse and say, oh, I need X number of this, I need X number of this, do that, and we could just like keep track of our total as we go. So the idea, we want to binary search on the number of metal and greedily make as much metal as we know we need at any point. I think we might need the binary search because otherwise do it step by step and make one metal, and you could just use one of your metals each time. Maybe you can, I don't know. I think I'm just going with binary search. I think that's simpler. But maybe you don't need binary search. I wasn't thinking about it. I think that would work. But I think we'll come back to this. I think it's wise to go back and try to implement Photoshoot. Because now that we've read all the problems, we know them all in the back of our head. We can think about it as we need. So I guess this should be bigger. I'm sorry if this is a little small. But it's a little more readable. Okay, so we'll make our source file bigger. Okay. So we'll do the same template. So we want to take in the input. And this is the number of cows. Read the cows. So we can take them in and then the breeds. So now we want to look at all pairs, count number of switches. So we can keep track of Boolean found equals false. So if we have seen no HG or GH pair so far, Boolean last equals false, whether the last pair is HG, true except false. So we'll just use a Boolean to keep track of whether the last pair we saw is HG or GH. We also want to keep track of the int splits equals 0, count number of switches from HG to GH. So what we want to do is we want to loop over all pairs. So this is for I equals 0, I less than n, I plus equals 2. So we skip. So Boolean type of this pair, whether it's HG or GH. So if we want to ignore HH or GG, if S of I equals S of I plus 1, then continue. We want to ignore those. Otherwise, we want to know the type. Corresponds. So HG is true because H would come first, otherwise GH is false. So if not found, then we'll just make found true and last equals type. So there's no split so far. Otherwise, found is already true, so last equals type, but if type not equal last, split plus plus. Split plus plus. Switched. I think now we can compute answer. So the ants is equal to the number of splits. But if, so the rule we saw was if we end in a one that is invalid, we need to still do one more split. So this is like the K and the two cases at K. So if last is false, because you still need one more split, and plus plus, and then we'll just output the answer. It was actually a very short implementation. I mean, I think it's a cute problem, but if this is correct, they're not like I may have gotten this is really easy to get off by 1 because of course we're dealing with, you know, I could have gotten this booleans just slightly off. It's the wrong file, but either way, I ran the correct file. I just had to mark it off. We could test this further, but again, there's really no harm in submitting. And just because of the ease of submitting, I'm going to submit A instead of testing. And there's a chance I just got off by 1. That's kind of sad, but we can just see whether it actually does. We try to be careful implementing, of course, but you know, it's possibly made a mistake. And it looks like we were correct. So that's pretty good. Okay, so that problem went pretty well. This is, of course, probably the shortest problem that we're going to implement today. But that one's definitely hard to notice. You definitely have to just mess around with cases and kind of try to figure out what doesn't change and what changed. So whenever you see a problem where you don't want to start, try to look for things that are invariant, try to look for things that don't change, try to mess around with inputs. You know, we were able to come up with this in a pretty reasonable way. So now we'll look at Alchemy. So we did go over the idea. We want to try to do this binary search. The upper limit for the binary search will be 10 to the 6 because that's the maximum number of metals you could ever have. So we're going to have to recursively implement this greedy approach. And modify current metals in place. So that means we're not gonna actually modify, we're not gonna like create a new list every time. We'll actually just like change the number we have at each step. So I think we have the idea. This might be a bit longer, but we can try implementing this and see how it goes. Make this bigger for us. So we're gonna start with a basic template. Okay, so we need to store a few things. We're gonna need the n number of metals. In counts or metal counts, which goes up to 100. The current inventory of metals. And then we want to store our recipes. So we'll want to make a struct recipe. Store recipes, max recipes. The maximum of recipes you have is, well, let's just land. I'm not gonna make a variable. So the recipe does not exist, but and of course, this greedy doesn't work because another observation you want to notice is that like the graph, like you're always going to decrease in size, and so it's like a DAG. So do make sure the runtime because yeah, you only recurse down this tree once, and the tree could be of size. I guess it could branch a lot. We might need to be wait. No, I think we're fine. We do want to be careful at runtime. So we want a function to make x of a given metal. So we can do something like void make metal and amount. This is gonna be our key function. This is gonna be our key recursive function. I mean, most of the implementation will be right here. And so we're gonna want to take in the input. Start writing that. Metal counts. So for the recipe, we want to know int makes, or I guess int result. And then vector int ingredients. M ingredients are given. We don't have to store M. And we know the results are unique, and we know this creates a DAG. So, but when I say DAG, like I mean directed acyclic graph, there's no cycles. Like you can't use a metal to make itself because you only go down in value, right? Even if you're not familiar with the term DAG. So now we want to take in the recipes. We didn't actually store the number of recipes. There's still at most n recipes, but we do want to actually store the recipes. Because we might actually want to store the recipe for the result at a given. I'll just do it. So we're going to make sure index the recipes, just make our arrays a little easier. So in this case, we want to know the result. We're going to know ingredients, then we'll have M, where M is the number of ingredients. So we'll take in the result, we'll take an M. So we'll zero index it, and then we'll loop over ingredients. Plus int ingred. And then we'll add it to our ingredients. So recipes of result. We're going to store recipes at the result location. Making it easier to look up for a given recipe. What's the, for given like result, what's the recipe that makes it? I guess, yeah, we can check the default value. And ingrids will be empty, so because it will initialize that way. So recipes of result can be recipe result ingrids. That. So now we need to binary search over possible amount of metal N. So int low equals 0, high equals 1 million. Ever have, since the metals are decreasing, we know that must be true. I'll do the binary search I use input. Of course, there's more than one input binary search. We do low plus I over 2. We're the best so far. So I guess in this case, we want to be able to reset our, okay. So the amount of metal N. So we'll check whether this amount is possible. So if works of mid we want to one, increase ants, and then low equals mid plus one. Otherwise, high equals mid minus one. We start ants at 0 because that's always going to be an answer, right? You could always just make 0. And then we'll output answer. Okay, so we have a couple of functions to fill in, but we've designed it in a way that this shouldn't be too bad. So we will need to copy over amounts to a temporary array. So we can make another array, current amount for each step. So we can copy it over. And then we'll recursively make as much. So we can just have this function return whether it exceeds. So I guess it'll return make n minus 1, because that is the maximum metal, and amount. So we'll see what our current is metal counts of metal and needed, which would be check if we already have enough. So if cur greater amount, we can just return true, but update our counts. So in this case, I need to make sure that we use cur counts. We'll use what we have when possible. And then otherwise, we want to use the amount we want to make the amount we need. So must use the recipe times, which means, okay, so the other case is check if a recipe doesn't exist. So if recipe is a metal dot ingredient dot size 0, no recipe, we just have to return false. Cannot make it, right? Because needed is greater than 0. We're stuck. So we'll make the ingredients. So first, in this case, we'll call Boolean works equal. I guess we don't name it works, but make rest. We want to get this ingredient, the ingredient I. We want to make needed of them. And so if not rec, here we couldn't make ingredient or enough. Otherwise, it worked if no. In this case, we never actually increase the amounts. We just pretend that we made it and then we use it. That might work. Here it's so it's not the warning, but it does output 1. It's possible this works. I'm not actually positive at the runtime, but we'll just go with it and see what happens. Okay. So for some reason, I failed 5 through 7. passed quite a lot of test cases. I'm not sure. Hmm. Hmm. Okay. I did pass quite a lot of test cases. That's a little surprising. Maybe that makes me think it might be some sort of smaller bug. Like, it seems a little less likely that would occur, but why those 3 test cases? Hmm. I'm just thinking, I wonder if we're over or underestimating. I would assume we're underestimating. Another thing we can do to see, maybe we can try binary search and just see if we can get. So while it keeps working, we'll just do that and we'll ignore the binary search. And try something like that and just see. Of course, we're at time limit. Maybe Tilly. Let's just try something. See if we can use the judge to help us debug. Okay, well, the interesting thing is, one, that runs in time, so we definitely could have probably proven something at the runtime. Like even on the test case 3, where it's 795, that worked fine. There's really not much to about the runtime. And this is even more efficient than doing it 1 by 1. We actually redid work and like copying and stuff. So this is actually particularly slow and it still worked. So that rules out the binary search. Another thing we can do, we can add some asserts. Asserts are a great way to debug. So assert I less than. So we'll assert not works. Bye-bye. And no, of course, we can always try generating a test case. The thing is, it's hard to probably generate. I don't think test case 5, 6, and 7 are actually small. So it might be a little hard to obviously know what's going wrong and be able to generate a test case. It's even slower, so it might kill you. And we do get runtime error. Okay, so that actually tells us quite a lot. That tells us that this assert is failing. So maybe it's not monotonic. That would not make sense though. So we must be doing something wrong. Okay. We made sure not to update metal counts. Or been a bug. And, you know, I didn't really expect that assert to fail. So it is good we wrote it because I was just trying to, then you know, the technique that you should probably do here is try to rule out things, to like try to rule out parts of the code that you want to ignore. Or maybe you just test an assumption. And here, it turns out that assumption's wrong. But I don't think it's wrong. I think I probably just failed to implement something correctly. So we are guaranteed there's only one recipe to make it. So of course we just want to greedily use that recipe. I'm curious what happens when we do that. If we, so for other cases too, because it definitely fails the 2 with the random error, but maybe it even fails more. Well, no, it can't. Yeah, I don't know. Never mind. That doesn't really tell us much. But there's a chance to pass one of those too. I'm just curious. This probably won't tell us very much though. That should be monotonic though, so I'm not sure what's happening there. Let's see, 5, 8, yeah. So for some reason, our mono, so this assumption is wrong. Another thing we can do is so try just using make. So while we can still make one, we'll make one. Thing is, we have to copy this over to begin with. So that works on the temple. It does. So now we limited this function. You know, So doing it one by one, which I wanted to do the binary search because I was like, maybe this is a little slow. Wasn't really keen in analyzing the runtime. And I was just willing to just test it. And we see that I guess let me think. I guess there is a wrong assumption there. I'm trying to think why that is incorrect. Maybe the issue is because we might be recursing at multiple points at the same time, and the amount available is changing. So we might be like, the bug was probably because like we store the current count, we don't use it, and then like when we come back from the recursion, things have now changed. Some metals that were available are no longer available, and we assume that we already took that many. So I guess I think you might want to do is do this to begin with. Update here. Oh wait, we never updated that. Wait. Well, yeah. Okay, so yeah, we have a bug station, and I think that's probably the bug. I think it's cur, not amount. Probably still works in the sample. I do want to put back. I won't put back the binary search, but I will put back this and just check that one time. This still works. Let me submit it. Let's see what happens. Just because I'm curious. Like, of course, we've already solved everything, and so of course we don't have to continue testing. I think if we didn't want to, but this is a really slow one. But there you go. That's the bug. And now we can do our binary search. So I can actually see the runtime. I'll just submit it. And then we get really fast runtimes. So as expected, that's what we meant to originally point. So small bug. So that is the entire contest. This contest, of course we have 5 hours. We spent more time. Just make sure you read all problems and make sure you try to think about them all. You don't have to rush to implement the ones you know what to do. You definitely don't want to get like tunnel visioned into a single problem. So especially if you get stuck on it and you can't debug it, like always to move on. So I tried to like think about all of them before actually implementing any of them. This one ended up being the easiest, or at least the quickest for me to get. Of course, difficulty is subjective anyway. And then Photoshoot, I think this is actually a nice problem, but you really just have to take the time to think about examples to figure that out. And Alchemy. This one you got to make sure to notice what constraints we have in order to make this work. But essentially, it's just a greedy solution where we just want to greedily build each of them. So those are the 3 problems we had in this contest. I hope US Open went well for you guys in bronze. For those of you saying bronze, I hope it went well. This is the last contest of the season, so this will be the last contest we'll be recording too for the season. Hopefully this helped you guys. I hope this helped you kind of see how you want to approach problems, how you should prioritize your time. You don't need to rush into coding. Take your time implementing. I mean, you saw my implementations were pretty thorough with comments, and like you don't need to do that, but you have the time. USACO is not a time crunched contest in general. But yeah, that's all we have for today. So I'm going to end it here. Hopefully you guys felt this was useful. Thank you for watching.